So we talked about trading action, and we mentioned that in the portfolio state we call this method add asset. So in this video we're going to talk a little bit about what happens when we call add asset and how we actually write these portfolios to storage. So also wanted to point out this function call in batch action towards the end. So what we're doing here is we're checking that the account context has a bitmap currency ID of 0. So this signifies that the account is not using the bitmap portfolio, which would trigger a different type of trading action here. It is using the array type portfolio. So we will take a look at what this method does as well. So what this method does is it writes the portfolio state to storage and updates the account context accordingly. So we'll start with the portfolio handler. So when we come to this this place right here with the portfolio state, we'll already have had called build portfolio state earlier in batch action. That will have happened during the settlement check. So we can just quickly take a look at where that happens here. So when we settle the account, if required, and return the portfolio, we will check if we must settle the assets. If we do, this will return the portfolio state. If we don't need to settle assets, what we'll do is we'll call build portfolio state. So build portfolio state happens here now. It's a little bit different than just reading an array from like using Solidity from storage. The reasoning here is that, so the main two differences are that portfolios are not stored sorted in storage. That would be too expensive to resort the portfolio every time we wanted to store it, but we sort it in memory. And what that does is it gives us some nice properties that we can rely on when we go to analyze the portfolio and change it. So looking at get sorted portfolio, the first thing we do is we load this array. And let's take a look at that method here. So when we load the array, we actually pass in the length, and this is different from how you would sort of use the native Solidity loading of storage arrays. The reasoning here is that this is a bit of a gas optimization. So Solidity uses an entire 32-byte storage slot to store the length, which is expensive for simply storing a uint8 value. For us, storage arrays, these portfolio arrays won't go past a maximum of 16 assets. So we first load the storage slot. So we first calculate the storage slot based on the account and a constant. And then we'll iterate through that, and each slot, each offset from the slot will be an asset. So each asset will take up one storage word, one 32-byte word, and we'll unpack it here. And we'll save the actual storage slot address here, which we'll use later. And then we will do a quick sort in memory. So this will sort the assets based on an encoded ID that sorts it by these three values concatenated essentially. So we sort of know what order these assets will always be sorted in. And we'll use this assumption in many parts of the code. Now, I wanted to take a look at this method called add asset. So when we call add asset, what we do is we specify the currency ID, the maturity, these values that define an asset. And what we'll do is we'll try to merge that asset into the array. So looking here, so Fcash or liquidity tokens are going to be defined by their asset type. So Fcash is an asset type, and each liquidity token, the liquidity token for the 3-month market, for the 6-month market, 1-year market, etc., will also all be their own asset type. And there's currency ID and maturity. So within this grouping, when these are true, an asset is fungible with itself. So if you were to have 100 Fcash for DAI on a certain maturity, and then you were to then try to put negative 50 DAI, FDAI of that same maturity, you would actually net off the notional. So this is a way that you could remove or reduce your Fcash balance before maturity. Same thing happens with liquidity tokens. The only restriction is that the liquidity tokens cannot go below 0, whereas Fcash can. So if we are able to successfully merge it, we will assign the notional and we'll update this variable telling us that we've updated this particular storage slot. Now this is all happening in memory. This is not happening in storage at this point. So if we're able to merge it into the existing assets here, stored assets, then we can return. If we're unable to, then we'll try to merge it into the new assets. So these are assets that do not exist in storage, that have only recently been created by the current transaction. If we're not able to do that successfully, then what we'll have to do is append it to the new asset array. If we don't have enough slots in the new asset array, then we'll extend it. And extending it requires like a memory copy here, which is kind of expensive in Solidity. So we want to avoid that if we can. And the rest of this is really just kind of setting all the variables for the new asset. Now we'll look at store assets. So store assets is not called directly, but we'll look at this store assets and update context method in a second here. But when we call store assets, the goal here is to essentially store the portfolio into storage the way we have it set up, and then return a number of variables that help us sort of better understand the context of the portfolio. So we'll talk about these in a bit, but let's first just look at storing assets. So the first thing that we want to do is loop through the stored assets array and ensure that anything that has a notional value of 0, essentially that has been net off exactly to 0, is deleted. And so this is something that we would actually do quite commonly. So in the UI, you may see a button like withdraw your loan. So what that does is, if you have a positive Fcash balance, what we'll do is borrow exactly that positive Fcash balance, so giving you an exactly negative Fcash balance, and then what you'll do is like essentially put that Fcash balance to 0 and be able to withdraw cash. And what that does is, if you've lent fixed for 6 months and you want to take your money out at 4 months, you basically borrow the exact amount of Fcash. Your asset will be deleted from your portfolio and you'll be able to take your cash out. So let's take a look at delete asset a little bit. So delete asset is looks a little bit involved, but once you understand it, it's not too bad. Deleting assets or deleting storage slots off of an array in Solidity requires sort of swapping 2 storage slots and deleting the last one. So essentially you can imagine if you have 4 slots in a storage array, you want to remove the last one and only have 3. Now it's possible that you want to delete the first storage slot in the array. So what you'll have to do is move the first storage slot, sort of swap the values in the first and the fourth, and then delete the fourth. So instead of actually touching storage when we do this, because it's possible that we'll be deleting multiple assets and we'll be touching storage again and again, we do this in memory, and then we'll flush it all at once in the next loop. So we have a variable on this store portfolio state that tracks how many stored assets we actually have, accounting for things that have been deleted. And then what we do here is we find the storage slot that's the max one, and that has not been deleted. So imagine that there's 4 storage slots. We've deleted the last one. So then the third storage slot is the max slot, and we'll go and set that here as a variable. So those storage slots are incrementing, and they're going to be like very large numbers, but they'll be incrementing. And because the portfolio is sorted in memory, it's not guaranteed that the last stored asset in this in-memory array is actually the one that has the maximum storage slot, right? So when they're stored in storage, they're in any order. And so we do need to check that we can find the asset that has the actual max storage slot here. If we are deleting the in the stored assets array, in the in-memory array, if we're deleting the one at the end, then we can just mark it as deleted. We don't need to do a swap. But if we are deleting a different one, then what we'll do is swap it. So we'll swap the storage slots here in memory. So like essentially pointers to storage slots of where this asset should actually be written to storage, and then we'll mark them accordingly as updated or deleted. So again, this happens all in memory. This is a pure function. And once we've done that, we will then loop through stored assets. And if the asset has been marked as deleted, we'll delete the storage slot. So we'll clear it out. And this is, and at this point, what we should have is that these storage slots are always at the end of the array. So we're reducing the storage slots from the largest one coming back down. If it's been marked as updated, we'll apply the updates and encode this in-memory object into a 32-byte word. So that's what will happen there. I'll come back to this in a second, but we'll also do something very similar for the new assets. We'll skip ones that have a notional of 0, so we won't even write those, and then we'll encode that, and the new assets will be appended to the end of the storage array from some offset here. So now we'll look at update portfolio context. So we should be running update portfolio context for every portfolio asset that we're writing to storage. So you see that we'll continue here, but here when this falls through, we will call update portfolio context once here and once here. What update portfolio context does is it calculates a number of summary variables for a portfolio. So we have the next settlement time, and what we'll do is we'll use this to check when the portfolio should next be settled. And what that does is it's a gas optimization, right? So we don't want to do a full settlement action if we know that the end result is nothing will be settled. So we'll get the settlement date for each asset as we write to storage, and we'll make sure that we have the minimum value here. The next check is this all-important has debt flag. So if any asset is negative, meaning a negative Ifcash, a borrow, we will set the has debt flag to true. And we'll also have this 32-byte sort of byte array, I guess, of the currencies. So the currencies in Notional are going to be stored as a uint16. So every 2 bytes of this 32-byte word is going to be a currency ID. And what we do here is we sort of pack up like all the active currencies that a portfolio has is active in, and what we'll do is summarize that in the count context handler. So we'll talk about that a little bit in a minute here. So when we exit store assets, we should have written all the portfolio assets that have changed to storage, and then we'll return these values. Now, store assets should only ever be called from this particular method in the account context handler, store assets and update context. Calling store assets without going through this method would not properly update these context variables, and that would cause problems. So we'll take a look at store assets and update context here. So we have an edge case during liquidation that it's possible, although quite unlikely, that the amount of assets would actually increase during liquidation. So we'll talk about this edge case when we talk about liquidation, but we do need to have this here. So only liquidation may allow the array to grow beyond what we're calling the max. And the maximum here is going to be 1 per tenor. So this is hard coded to 7 at this point. Here we are setting the has debt flag on the account context, depending on what the portfolio has said. So let's take a quick look at this. So you'll see that this has debt flag is actually 1 byte, and it has the 2 bits, that can possibly be set, so 2 flags. One is if there is a portfolio asset that has debt, and one is if any cash balance is negative. And we do this just so that we can distinguish between the two, because we update those 2 things differently. So note that in batch action, when we look at this, so if either one of those flags is set, then we will check free collateral. So this sets those flags, and then we'll also set the array length. So the next time we read the array, we will be able to read all the assets. This is quite important. This is returned from store assets, and this is settle time. So now we'll talk about active currencies. So active currencies might be a little bit hard to explain in a video, but I'll do my best here. So what active currencies is it's a 18 byte storage slot. Take a look at it here. It's an 18 byte storage slot, and it's also 18 bytes in memory. And what it represents is 9 total active currencies possible, with each being sort of a 2 byte position in this 18 byte array, essentially. So what we'll do here is so looking at it's a little bit hard to see here, but looking at a particular 2 byte section of active currencies, it's a uint16 with the top 2 flags set. So this is the top bit, and this is the second to top bit. The top bit being set will mean that this currency is actively in the portfolio, so it's actively an Ifcash asset or a liquidity token asset. And if the second bit is set, then it's active in a cash balance. So it's either actively in a asset cash balance or an end token balance. And so this is just a way for us to track where an account's assets are. And this unmasked flags is going to be, all the other bits below the top 2. And so this is going to be a little difficult to sort of explain in video, or I'll probably make a mistake. But you can read this comment and see the different sorts of possible outcomes from this search. So what we'll say is we have a particular currency without the flags set. We'll tell this method whether or not it should be active, and then which flag of these 2, active in portfolio or active in balances, are we talking about. And so what what this loop will do is it'll kind of look for one of these outcomes and sort of respond accordingly. So it's probably best just to look at this very carefully. But what is happening here is that we'll take all the currencies that this store assets is telling us are in the portfolio, and we'll loop through them and tell that particular method that currency should be set active to in the portfolio. And we'll do a little bit of optimization here, so if they're the same, we don't need to do it twice. And you'll notice like the way we loop here is to shift down 16 bits each time. So that is how we update a portfolio asset. So that will be finalized here. So we'll talk about settlement in this video. In batch balance and trade action, we first settle the count if required, and we'll make a similar call in many of the other actions. So you'll see in batch balance action, we make the same call. Now looking at this internal function, what we'll do is we'll first check if an account must be settled, and if we do, we'll make a call to this external library to settle the assets. This check here is quite simple. So if we look at must settle assets, it simply looks at the settled time, the next settlement time, and compares it to the current block timestamp. When we look at this library, this settle assets external library, we'll see that there are a number of external functions that essentially all do the same thing, but return different combinations of these three variables. And this is really just a gas optimization. We don't want to do multiple storage writes if we can help it. So if, say, in batch trade action, we need to access the portfolio, we'll have it return the portfolio for us. If we don't need to access the portfolio in the action, then we can have it be stored here and not return it from the library. So looking at the settle account internal function here, we see that settling accounts is different for the bitmap portfolio and for the array type portfolio. So in this video, we'll talk about the array type portfolio and talk about the bitmap portfolio in a separate video. So settling portfolio assets is implemented in the settle portfolio assets internal library. Here we call settle portfolio with the portfolio state, and the first thing we'll do is get this settle amount array. So the settle amount array is pretty simple. It's a currency ID and a net cash change. So for positive Ifcash, we'll have a positive cash change. For negative Ifcash, we'll have a negative balance change. Now, since in Solidity it's not very easy to provision dynamic arrays, we'll first provision the settle amount array before we start to iterate. So what that entails is looking at every asset and determining if it needs to be settled. So looking at asset handler, we have a function here that calculates the settlement date. Now the settlement date for Ifcash is maturity. So we see that here. Also for the 3-month token, 3-month liquidity token, it's also at maturity. So we'll return maturity here. Now, liquidity tokens settle differently from Ifcash. Liquidity tokens settle every 90 days. So if you're trading Ifcash on the 1-year market, the Ifcash will settle 1 year from now. Now, for a liquidity token in the 1-year Ifcash market, it'll settle every 90 days. The reasoning for this is that when the Ifcash market, which is at 1 year, begins trading, it will be at 1 year, but over time, it sort of decays down less and less as it gets closer to maturity. So by 9 months, it's 90 days away from its sort of tenor, which is 1 year. So if you're trading Ifcash there, you're actually only getting 9 months of Ifcash. And so for longer term maturities, this really becomes a problem. And so what we do in Notional is we reset the market back to 1 year every quarter, so every 90 days. And therefore, all the liquidity tokens that are sitting in that particular Ifcash market will get settled down to its components, to cash and Ifcash at 90 days. So we'll look at how that works inside portfolio assets here. Now, settling a portfolio will then, so now that we have the settle amounts here, this array provisioned, we will then loop through the portfolio again, looking at the assets that need to be settled. Now, since we know that we've loaded the portfolio from storage and it's sorted every time, we can rely on the fact that if the currency ID does not match, that means we are now in a new currency. So we can increment the settle amount index and move on to the next one. So this is an area where having a sorted portfolio makes things a lot easier for us. Next thing we have is the settlement rate. So we're going to go get that. Now the settlement rate is the exchange rate between the Ifcash underlying DAI and C DAI for a particular maturity. Now, the way this works is that we use a single settlement rate for all assets of a given currency maturity combination. So all Ifcash that are defined by these two identifiers will have the same settlement rate once the maturity is passed. So that means that all the positive and negative Ifcash will settle to offsetting balances of positive and negative C tokens. So this build settlement rate stateful is in the asset rate.sol file. The asset rate.sol file is simply a library that handles conversions from C token denominations to underlying denominations, and it'll go both ways. So for the settlement rate stateful, it'll check if the rate has been set. If it hasn't been set, it'll go get the current settlement rate and set it here and emit event. Otherwise, it'll simply get the rate that's been set. So once we have the settlement rate for Ifcash, it's pretty simple. We'll simply convert from underlying, so from DAI into a C DAI balance at the settlement rate, and we'll delete the asset. If we have a liquidity token, we need to check if the maturity of the liquidity token is past the block time. And what that means is if that is true, that means we will have an Ifcash residual as a result of settling this liquidity token. If it's not true, we can simply settle the liquidity token to cash. So let's take a look at these two functions and see how they behave. So in either case, the first thing we do is we go get the market object. So we call market.getSettlement market. The difference between this and regular load market is that we can specify a settlement date, so we can go arbitrarily far in the past to get a market that is in the past. Essentially, that's already been settled. We'll calculate how much cash and Ifcash this liquidity token has a claim to, and update this settled market state to account for removing these assets. Now, like I said, if the liquidity token itself, the Ifcash, has matured, we can simply convert that to underlying, convert the Ifcash to an asset cash balance, and return that. Now, for the liquidity token that settles to an Ifcash residual, when this will happen is if you have a liquidity token in the 1 year Ifcash market. When that settles, it's going to be 9-month Ifcash and asset cash and C tokens. So the 9-month asset cash is going to remain in the portfolio, the 9-month Ifcash is going to remain in the portfolio as a residual. So in this method here, what we do is we again rely on the portfolio being sorted, and we can check the previous asset to the liquidity token, which based on the way we sort will be the corresponding Ifcash asset that we can net off against, and we will check that here. If it does not exist, we will convert the liquidity token into an Ifcash asset and store its notional. So you can look at this very carefully, but essentially what we're looking at here is, in most cases, when you provide liquidity, there will be a negative Ifcash asset that pairs with the liquidity token. And we discussed this in the Ifcash markets video. And when you remove the liquidity, when we settle the liquidity out, the positive amount of Ifcash claim that the liquidity token has will net off against this particular Ifcash asset. When all this is done, we will set the market storage and then update the settle amounts object with the net amount of cash change. So we've discussed execute trades array batch and how that is ultimately finalized in store assets and update context. Now we'll look at the Bitmapped currency portfolio and how it's updated when we execute trades on a Bitmapped portfolio. So taking a look at this first, we'll see that if the Bitmapped currency ID is set to non-zero value, we'll check that the Bitmapped currency equals the current currency of the action. So you cannot trade Ifcash or hold Ifcash assets for any currency other than the Bitmapped currency that is set on the account. And so what this does is it enables an account to hold more assets in a bit more storage efficient manner for a single currency, but it does not allow them to hold Ifcash assets for other currencies. So they can hold cash balances, they can hold ETH or NETH, N-token ETH as collateral against perhaps borrowing in a particular currency, but they can't hold Ifcash assets in any other currency. So now we'll go into execute trades for the Bitmapped in trading action. And what we see here is that we get this assets bitmap from the Bitmapped assets handler. We'll go ahead and execute all the trades here. So notice that this loop does not allow for executing liquidity token trades. So these will only be Ifcash trades in the loop. And then we'll add that Ifcash asset here. It's called an Ifcash asset, but we'll add it to the account. And then we'll finally set the bitmap here before we exit. So this bitmap, how it works and how it's configured is best described in the white paper in Appendix B here. So the bitmap is a 256-bit bitmap. So each bit, if it's turned on, signifies whether or not there is an Ifcash asset. Here we're calling it Ifcash, which means idiosyncratic Ifcash, meaning Ifcash that can exist on dates that are not being actively traded by Ifcash markets. So each bit, if it's set to 1, will signify that there is an Ifcash asset at a particular relative date to the next settle date. So, and then there's a mapping. This is a solidity mapping from a particular maturity, an absolute time point, to the notional Ifcash map. So you can take a look at this. So each section of this bitmap is assigned sort of a time granularity. So the first 90 bits each represent a single day. So, and then so this represents the first 90 days. From 91 to 135, this represents 360 days. So in Notional, we use 360 days to represent a year. And we use 6-day weeks here, so not 7 days. The reasoning for this is that 6, 90, 360 all divide evenly into each other. And so we can guarantee that when we do the modulo here, there will always be sort of a lower level bit that will map to a higher level bit. That these dates will always map to each other. And we discussed this a little bit here in mapping on roll down, what that means. Then we have more bits. This represents up to 6 years, and then this finally, the last section of the map will represent out to about 20 years, a little bit more than 20 years. So in here we have some Python pseudocode that sort of does the math, that represents how you would do the math to translate a bit number given the sort of this initial date, the relative, to get the relative maturity from a particular bit num, and the inverse here. So one thing to note here is that these bits are one indexed here, so there is no 0 bit, and that was just made it a little bit easier to work with the math here. So this date math here is implemented in datetime. So you'll see this get bit num from maturity and get maturity from bit num, and this is just the math that we talk about in the white paper. The constants are defined here. So you'll note that a week is 6 days and a year is 360 days. So these are not exactly calendar days, and there's a reasoning here that these all divide evenly into each other. So coming back to trading action, we can take a look at these methods on the Bitmapped asset handler file, the library. This is also in the portfolio subfolder here. So starting at the top, we will get the assets bitmap. This is pretty simple. It's a single storage word, 32 bytes. So we'll just retrieve it. Nothing too fancy there. Setting it is equally straightforward. We check how many bits are set, representing how many Ifcash assets exist, and that can't be over this constant. So currently it's set to 20, and over time we may increase that if we feel like that's necessary. Getting the Ifcash slot, which is the mapping which has the notional amount for a particular Ifcash asset, is done this way. This is essentially a Solidity mapping from the account to the currency ID and the maturity to right now this is encoded as 32 byte word, but it's converted to in 256 notional. So whether you're adding multiple assets or a single asset, you kind of pass through this add Ifcash asset method. And what we do here is we go get the slot. So knowing the maturity, we go get that and the currency ID. So the slot will sort of always be set no matter where the asset bitmap is, where this assets bitmap is. So we don't need to move this mapping as time passes. So this Ifcash slot is set at an absolute time. Now, given the next settle time and the maturity of the asset, we will get which bit number in the bitmap is represented by this particular maturity. So knowing the number of the bit, we'll check if it's set to 1 or 0. If it is, then we will read the existing amount, the existing notional amount from the Ifcash slot. We'll net it off with the new notional amount that we want to update here. And here we require that it's less than this particular bounds, and then we'll store it. If the existing notional, if the new notional here after netting is 0, that will mean that this slot will get cleared, and we'll also want to turn off this bit so that we don't check this value again. We'll return the bitmap, so this is modified in in memory here, and we'll return the amount, the new amount of this particular Ifcash asset. If the bit isn't set, so if we're looking at this asset bitmap, if it's not set and the notional is a non-zero value, what we'll do is we will store this at the slot. We'll store the notional value at the slot, and we'll turn the bit on, and then similarly return those values. So you can see that although there's a lot more math involved with dealing with these Ifcash, these bitmap portfolios, actually doing these updates is a lot simpler. So when we come back into trading action, when we complete this loop, we will have set in storage these Ifcash amounts. So we don't need to do that in batch action. We don't need to finalize those. However, this has only been updated in memory, so we'll go ahead and set that here to kind of finalize this in storage. So that covers how we update the bitmap portfolio type. We'll talk about how we value assets in a separate video. So now we'll talk about settling bitmapped accounts. So if an account is bitmapped, we will enter this method here on settle assets external. And what we'll do is we'll settle the bitmapped account here, and then we will set the next settle time to the new settle time, which will be this block time at UTC 0. So that's like the current block time backed up to UTC 0 midnight. We'll set the bitmap, and then since the bitmap portfolio only ever holds one currency, we know that the settled cash is just always in this one currency. So let's take a look at this settled bitmap cash group method. So what happens here is we have the old settle time. So this is what is currently set as next settle time on the account. And then we'll load the bitmap and do some checking here. So we'll get the new settle time, which is the UTC midnight value, sort of previous to the current block time. So that'll be the new settle time. So this will always be a little bit less than the block time. And then what we'll do is we'll get the bit number, what we call the last settle bit here. This is the bit number that represents the new settle time under the old settle time sort of reference point for the bitmap. So when we're thinking about settling bitmap portfolios, it's important to understand that the Ifcash mapping is sort of stored in absolute times. So an Ifcash asset maturing on Jan 1st, 2020 is stored at a storage slot referencing January 1, 2020. But the bitmaps, all the bits in the bitmap are set to 1 or 0, and they sort of reference a relative time to the next settle time stored in the account context. So when we calculate this new settle time, what we're getting are all the kind of bits in this bitmap that are now referenced like absolute points of time, like maturities that are in the past, right? All of these bits up into including last settle bit are less than new settle time, and so therefore we need to like go check all those bits to see if they contain Ifcash, and then settle that Ifcash to a cash balance. So we have a method on bitmap called getNextBitNum. So we'll take a look at that. So getNextBitNum simply does a most significant bit wise search here. So this is sort of a binary search over the bitmap to look for the most significant bit, and then we do a little bit of math here to translate that to like kind of flip the endian and make it one indexed, which is what we use here. So as long as the next bit number that is set is in this last settle bit range, what we'll do is simply go get its maturity, load its Ifcash position, and then turn it off and keep going in this loop. So settling is pretty simple, right? We'll load the notional amount, we'll convert it, from underlying to asset cache and delete it here. And then opposite, so when we want to, so now that what we're gonna do is we're gonna set a new settle time that's this value. So we'll have to remap all the bits that are turned on to reference like this new relative time, the new settle time. So that's also fairly simple here. We're gonna create a new bitmap. We're gonna iterate through and get the maturity for that particular bit num that is set, and then we're gonna get what bit number that is now under the new settle time. That maturity represents under the new settle time. We'll set it to true, turn it off here, and then we'll just loop until we're done. So as you can see, this is like quite simple, and that's kind of one of the nice things about working with these bitmap portfolios.